NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will build an intuitive and visual proof for two beautiful identities about floor functions of square roots and cube roots, and we will summarize them into simple, easy-to-remember formulas. We start with the core example for square roots, exactly as written here. Key rule: the floor of square root of k equals n if and only if k lies between n squared and the next perfect square, not including it. Step 1. Identify the constant floor value on the entire interval for all integers k from n squared up to, but not including, the next perfect square. The floor of square root of k stays equal to n. Let us visualize the interval on a number line from n squared on the left to just before the next perfect square. Every k in this block has the same floor of square root equal to n. Quick challenge: if n equals 4, what are the first and last integers in this block? Take a moment to think. Now we count how many integers are in this interval. Step 2. The number of integers from n squared up to 1 less than the next perfect square is last minus first plus 1. That is, open parenthesis, n plus 1 squared minus 1 close parenthesis minus n squared plus 1. This simplifies to 2n plus 1. Check with small values. For n equals 1, we have 1 squared to 3. That is 3 terms. For n equals 2, from 4 to 8, that is 5 terms, matching 2n plus 1. To sum a constant value, simply multiply the constant by how many times it appears. Step 3. Every term equals n, and there are 2n plus 1 of them. So the total sum is n times open parenthesis, 2n plus 1, close parenthesis. The exact same idea works for cube roots. Here, the block length is open parenthesis n plus 1 cubed minus 1, close parenthesis minus n cubed plus 1, which simplifies to 3n squared plus 3n plus 1. Since every term equals n, the sum is n times 3n squared plus 3n plus 1. Final results: for square roots, n times 2n plus 1. For cube roots, n times 3n squared plus 3n plus 1. Summary: the floor value of a root stays constant between consecutive perfect powers. The number of integers in the square root block is 2n plus 1. The number in the cube root block is 3n squared plus 3n plus 1. The sums are simply constant times the block length. We will evaluate a bracketed square root, sum using the floor function, also called the bracket function. First, we show the example. Then, we display the expression to evaluate. Step 1. We will evaluate each floor bracket individually using the definition of the floor function. The floor of x equals n, where n is the greatest integer less than or equal to x. Now, we compute each bracket value. Everything from square root of 4 to square root of 8 lies between 2 and 3. Therefore, each floor bracket equals 2. Step 2. We now add the constant values. The sum of a constant repeated n times equals that constant times n. We replace each bracket by 2 and add them up efficiently by multiplication. We are going to evaluate a sum of floors of square roots from 64 to 80. I'll show you an easy pattern to turn this long sum into a quick calculation. First, let's display the word example. Now, here is the problem statement. Step 1. Identify the constant value of the floor terms. There is a key rule here. For every integer, n, all square roots from n squared up to the next perfect square minus 1 have the same floor value, namely n. Let's add the step title on screen. In our problem, the first term is the floor of the square root of 64, and 64 equals 8 squared, so n is 8. The next perfect square is 9 squared, which is 81, so the range goes up to 80, which is 1 less than 81. Therefore, every term from the floor of square root of 64 up to the floor of square root of 80 is equal to 8. Quick challenge: how many terms are in this block from 8 squared to 9 squared minus 1? Step 2. Apply the summation formula. The block from n squared through the next perfect square minus 1 contains 2n plus 1 terms, and each term equals n. So the sum over that entire block is n times quantity, 2n plus 1. Let's add the step title on screen. Since n equals 8 here, The number of terms is 2 times 8 plus 1, which is 17, and each term is 8. So S equals 8 times 17. Step 3. Compute the product. We now multiply 8 by 17 to get the total. Let's add the step title on screen. 8 times 17 equals 136. In this walkthrough, we will solve a floor of square root summation example using clear, numbered steps and rule boxes, with key changes highlighted in orange. We start with the key rule for floors of square roots. We group integers x by the interval where the floor of root x is constant. Step 1. Find all x with floor of root x equal to 1, that is from 1 squared through less than 2 squared, or 1 through 3. Next, apply the same rule with n equals 2. Step 2. All x with floor of root x equal to 2 lie from 4 through 8 inclusive, and again for n equals 3. Step 3x ranges from 9 up to 15 for our sum, because it stops at 15. Now we use grouping to turn the sum into counts times values. Group terms by constant values, 3 1s, 5 2s, and 7 3s. Finally, add the products together. 3 plus 10 plus 21 equals 34. That is our final result. Here is a quick sum result. We state the problem in bold orange math. Capital T equals the sum from 1 to 625 of the floor of the square root of I. Rule: floor function groups. We group terms where the floor of the square root equals the same integer, n. Step 1. Group terms by their floor values. Visually, each integer n repeats for inputs from n squared to n plus 1 squared minus 1. Rule: count of terms in each group. The count from n squared to n plus 1 squared minus 1 equals 2n plus 1. Step 2. Multiply the floor value n by how many times it occurs, which is 2n plus 1. We also keep the last term for 25 squared separate. Rule: sigma notation. We can replace the repeated pattern by a summation. Step 3. Convert the series to sigma notation. We write t equals the sum from n equals 1 to 24 of n times 2n plus 1, then plus 25. Rule: linearity of summation. The sum of a plus b equals the sum of a plus the sum of b, and constants can factor out. Step 4. Distribute inside, and split the sum into two pieces. That yields 2 times the sum of n squared plus the sum of n, then plus 25. Rule: some formulas. The sum of n squared equals n times n plus 1 times 2n plus 1 divided by 6, and the sum of n equals n times n plus 1 divided by 2. Step 5. Apply the standard formulas. Step 6. Substitute n equals 24. Substitute n equals 24 into the formulas. Step 7. Simplify the arithmetic. 2 times 24 times 25 times 49 over 6 is 9,800, and 24 times 25 over 2 is 300. Let us also pause briefly for a quick check. Step 8. Final addition. The result for t is 10,125. Let us wrap up with a quick summary and a practice suggestion. We now apply the rule for the sum of floors of square roots on a complete square interval. Step 1. Apply the summation formula. Here we rewrite the series using the rule. Quick challenge. Can you identify n from the starting term square root of 81? Now we perform substitution for n equals 9. Step 2. Substitute n equals 9 into the expression. We highlight the changed part in orange. We now multiply to get the final product. In orange. We now multiply to get the final product. Step 3. Calculate the final product. We multiply 9 and 19 to find 171. We will process the floor of square root sum exactly as shown in the instructions, following the same steps and grouping. First, we show the word example by step with rule boxes and clear explanations. Rule box: floor function bracket definition. Now step 1. Calculate all terms where the floor equals 1. Quick challenge. Which integers x satisfy 1 less than or equal to the square root of x is less than 2? We evaluate bracket square root 1, bracket square root 2, and bracket square root 3, each equals 1, so the sum is 3. Rule box: floor value transition for 2. Step 2. Compute all terms where the floor equals 2. Tip: there are 5 terms in this group, from 4 through 8 inclusive. We add bracket square root 4 through bracket square root 8, each equals 2, so the sum is 10. Rule box, floor value transition for 3. Step 3. Compute all terms where the floor equals 3. Note, we include 9 up through 15, giving 7 terms. Each equals 3, so the sum is 21. Rule box, summation of parts. Step 4. Step 4. Combine all partial sums for the final result. Pause and add the 3 values. We obtain 34. Finally, present the answer in green with the confetti brackets. Now, we wrap up with a concise summary. Counterclockwise arrows button, quick recap done. Take a moment to write your own grouping for 24. Ask questions anytime. And keep practicing. And keep practicing. In this lesson, we will solve a beautiful floor function sum involving square roots, and then find prime pairs x and y that satisfy the equation. Let's start with the example and the problem statement on screen. We want to solve the sum of floors from square root of 1 up to square root of x squared minus 1 equals y. We will derive a closed form in terms of x, and then test prime x values to see when y is prime. Key idea. For any integer n, every integer k from n squared to 1 less than n plus 1 squared has floor of square root equal to n. That is, the floor of square root stays constant in that whole block. Now group the original sum by these constant blocks. The numbers from 1 up to x squared minus 1 split into blocks for n equals 1 up to x minus 1. Each block contributes n repeated to n plus 1 times. So the total becomes the sum from n equals 1 to x minus 1 of n times 2n plus 1. Expand n times 2n plus 1 into 2 times n squared plus n. Then apply the standard power sum formulas for the sum of n and the sum of n squared, with k equal to x minus 1. We get 2 times the sum of n squared plus the sum of n. Using the formulas, this equals 2 times x minus 1 times x times 2x minus 1 over 6, plus x minus 1 times x over 2. Now simplify. First combine over 6, factor out x times x minus 1, and notice 4x plus 1 appears. In factored form, the sum equals x times x minus 1 times 4x plus 1, all over 6. Expanded, this is x times 4x squared minus 3x minus 1, all over 6. Set the sum equal to y. That gives y equals x times 4x squared minus 3x minus 1 over 6. We will search for prime x, giving prime y. Try x equals 2. Then try x equals 3. We will also observe that the next prime x equals 5 gives a composite y. As a quick verification for x equals 3, the sum from k equals 1 to 8 of floor of square root of k is 1 plus 1 plus 1, then 2 plus 2 plus 2 plus 2, and finally 2, which totals 13. Therefore, the prime pairs that satisfy the equation are x equals 2, y equals 3, and x equals 3, y equals 13. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.